So let's talk about section 5.1, discrete random variables. Now with this, we are using a lot of our knowledge from previous chapters to help us through this. But we do have a few new terminologies. So our first new terminology is random variable. Now a random variable is a variable whose numeric value is determined by the outcomes of a probability experiment. Now normally when we talk about variables, a lot of people think algebra and the notation of x. We are going to use the notation of x, but again, this is more of a notation. It is literally there to kind of help us with the idea of what we're actually doing. Okay? So what we're going to do is if you see an uppercase x, that's going to represent the random variable itself, and a lowercase x is going to represent our specific value in the random variable. So think of basically as big X as these are the words in the problem. Okay, so normally when we think about them, I need you to kind of think more about these are the words actually in the problem itself. And then think of little x as a specific value, so like just a number or some specific outcome. And normally these are kind of more in reference to the actual event itself, the specific outcome in the event. With the words in the problem, this is referring to like all in the sample space. So like all outcomes in that sample space itself. But because there's so many of them, we only really talk about them in terms of words. Now, kind of get familiar with this big X and little x because this is going to follow us through a lot of the other sections as we move up in upper chapters. This is also what they use a lot in a lot of definitions. So you're going to see this kind of notation written out quite a bit. So our first definition is a probability distribution. Now, we've talked about a frequency distribution, and a frequency distribution is just basically a table with a bunch of frequencies on it. A probability distribution is going to be the same. It's going to be a table. Now, sometimes it can be a formula, but it basically gives the probabilities for every value in some random variable x. Now, there is a couple of properties to this. Our first property is it's a probability. And we know that all probabilities have to be between 0 and 1 inclusively. Okay. The second thing we know about a probability distribution, so in specific reference to a table, is that the sum of all the probabilities has to equal 1. Okay. So again, you'll see in those definitions, we've already started using that big X and little x in making reference to in general. But let's actually give a specific example. So let's take a peek at, we're going to create a discrete probability distribution for x, and our x, our random variable, is going to be the sum of 2 rolled dice. Okay, so x itself is the sum of 2 rolled dice. So we're going to begin by listing every possibility that we could have for those sums. So when I start to think about this, think about it in terms of when I talk about big X, this is all of these. And I can't list out every single one of these. So what I do is instead of listing out all of them, I'm just going to list out saying that big X is going to be the sum of all of 2 dice being rolled. And little x is making reference to just like 2 or 3 or 4 or 5. So little x is making reference to that individual event itself. Okay, so to help us out, let's actually look at this in terms of a little bit more in with like, what are those different possibilities? So when rolling those 2 dice, there are 36 possible rolls, because remember, you've got 6 times 6, which is why we have 36 different outcomes. Now, each one of those has a sum, and when I looked at all the sums, they only went between 2 and 12 inclusively. So they included 2 and 12. But we had no chance of getting a 1. We had no chance of getting a 0. We had no chance of getting 13s. But we know all of our little x values are between 2 and 12. So to find our probability distribution, this here, for this problem in particular, we'll actually have to create the probability for each one of those based upon what we know. Now, the probability of getting a 2 as a sum is going to be 1 out of 36 because there's only one way in which you can get a sum of 2. Now, the probability of getting a sum of 3 from rolling the 2 die is 2 out of 36 because there is 3 is basically 1 plus 2 or 2 plus 1. So there's 2 ways in which I can get that sum of 3. Now, understand that we're going to have to continue this process all the way down for each one of those outcomes of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, which were the sums that I could have. Now, if I do all that up, I'm going to see here is a probability distribution for all of this. Now, I am going to kind of bring attention to one or two things. So you'll notice here that like 2 over 36, 3 over 36, 4 over 36, and 6 over 36. These items here, I could actually simplify a little bit further. So most of the time, if this was my final answer, I would simplify these fractions all the way down. However, because this is kind of a teaching method right now, I am not going to simplify them down because I'm about to show you a little trick here. But I wanted you guys to see this to make sure that you're kind of understanding where they actually came from. Now, when I do take a peek at this, you will begin to notice that I have made reference to x here. And again, little x is these are all of those possible outcomes I can get. And then the probability of our event where we have that little x. So this is that kind of reference to say, what is the probability of rolling a 2? What is the probability of rolling a 3? Now I'm going to use little x in reference of saying that basically go back to here is what these are changing based upon. Okay, so when we check these, now we can check these all out ourselves if we wanted to, going back to a couple of slides previously where we looked at all of these different outcomes and count them up. Okay, however, when I take a peek at this, one of the things that I kind of want to notice is none of these are bigger than 1. And none of these are smaller than 0. So all of my probabilities are between 0 and 1. Okay. Now, I could technically include 0 or 1, but again, it's not necessarily in this case because we did not have any probabilities of 0 or probability of 1 happening. But we do see that all of these are between 0 and 1. I also want to note is that I know this specifically is considered a probability distribution because as I take a peek at this, I can literally add all of these ups going straight down. So if I were to add them all up, so if I were to take all of these and add them up going straight down, I'm going to end up with 36 over 36, which equals 1. And that right away tells me that we have a probability distribution. All of these numbers are between 0 and 1, and the complete sum of them is 1. So that lets me know that we do have a probability distribution. Okay? So just kind of keep in mind that when you see these notations here, these are literally just making reference in terms of things in general. So our properties of these probability distributions, just to remind yourself, is that everything has to be between 0 and 1. I can actually equal 1 and I can equal 0. And all of the probabilities added up together have to sum to be 1 if we are looking at a true probability distribution. So now that we've talked about probability distributions, let us talk about expected values. Now, normally when we talk about probability distributions, we switch up the word and we talk about this thing called an expected value, and it's basically, it's the mean. It's just, we don't like using the word mean when we talk about probabilities. It's what should we expect that probability to give out. So in this case here, we have a bit of that notation. Now, depending on what you're looking at, you're going to see these two notations here. And these two notations here are kind of the items that you want to remember. And again, just remember expected value is the mean. Now, I'm going to show you how to do this by hand, but then I'm going to show you a trick in the next problem that gets a bit more complicated by how do we do this without by hand, but using the calculator. But you should have an idea of this formula here this one's kind of a good one to keep in mind of where things are coming from in case you make a mistake for an expected value. Okay, so when calculating the expected value, again, you want to round to one decimal place more than the largest number of decimals in your given data. Again, occasional exceptions are made for this rule, but majority of the time, this is kind of our natural rounding scheme. Okay, so let's start with a problem. And again, it's got a lot of words to it, so don't freak out on this. So let's return to the booth at a state fair that has got rubber ducks floating in the water. Now, I'm going to pay $1, okay? And that $1 gets me 2 chances to win a small stuffed animal. That's worth $5. Now, by choosing a duck that has a star on the bottom, you get a small stuffed animal. Now, if you happen to manage as you pull, because you got 2 chances, right? What if I pull 2 ducks that both have stars drawn on them? Well, you win an extra large stuffed animal, and that's going to be worth $15. Now, after you do your first pick, the first pick you pick, the rubber duck is then placed back in the water before you pick again. Okay, and if there are 50 floating ducks, 3 will have stars drawn on them. So what is the expected value of this carnival game? So am I expecting to win or lose money on this game itself? Well, let's calculate it out. So as I take a peek at it, again, I'm looking for the expected value, meaning do I expect to win or lose this game? There are 3 possible outcomes. You either win a large stuffed animal, you win a small stuffed animal, or you don't win either. Now, in winning the large stuffed animal, you have to understand we're talking about winning, but there's a value connected to that winning, right? So the probability of winning the extra large stuffed animal is basically an independent event because you take the first duck, see what you got, put it back, and then choose your second duck. So realistically, these are independent events, so we can use our multiplication rule for probability here. And so picking a star duck is 3 out of 50. And then choosing a second duck that is got a star on it is still going to be 3 out of 50 because remember, we put it back. Okay, so our overall probability of getting 2 ducks with stars on it is going to be 9 out of 2,500. Now, again, we've already paid $1 for this game, right? And the extra large stuffed animal is worth $15. So realistically, I've already paid $1 on it. So I'm only getting $14 worth of stuff. Okay. Now, what if we don't win? Well, if we don't win, we know, again, still very similar to winning the extra large stuffed animal. There is 3 out of 50 that are winning. That means 47 out of 50 have no stars on them. And again, we are putting back each time. So 47 out of 50 times 47 out of 50, which means that probability is going to be 0.8836. And again, we paid $1, but we didn't win anything, so we're out $1. So since we're out money, I'm going to use a negative symbol there. Now, remember, I said there was 3 outcomes. So you could either win a large, a small, or not win at all. We've just figured out not winning and getting the large one. What about the small one? Now, for our small one, this one is a little bit more complicated, okay? Because I could get a star duck on the first draw, or I could get a star duck on the second draw, but I only get 1 star duck. Now, since we kind of know there's only 3 outcomes for this game, we're going to use a complement rule here because I don't really want to spend a lot of extra time figuring out probability. So I know that to get 1 star duck and 1 non-star duck, it's basically the only other probability I have left. So I'm going to say 1 minus, well, what's the probability of me getting 2 star ducks plus what's the probability of getting no star ducks? Add those up and subtract that from 1, and that's going to tell me the probability of getting 1 star and 1 non-star. So that's going to give me that 0.1128. Now again, we paid $1 to play this game. That small stuffed animal is only worth $5. So realistically, it's only worth $4 now because I paid $1 on it. Okay, we're going to put this all in a table and we're going to get out what our expected value is itself. Okay, so when we put it all together, we've got our winnings of each item here. Now I'm going to add in a little bit, so I'm going to remind you that this $14, this is our large stuffed animal. This is if we basically no win anything, and this one was if we had the small stuffed animal. Okay, and again, we're taking $1 off for each ticket here. So since the large stuffed animal was worth $15, but we paid $1 on it, it's technically only worth $14 now. Okay, same thing for if we win, we lose $1 then. So since we lose it, that's why it's negative. And the small stuffed animal was worth $5, but we pay $1 on it to play the game. So it's really only worth $4. Now we figured out the probability of each one of these. Okay, now this is where this part right here, this is what we would call our probability distribution table. Now to get my probability distribution table, we do want to basically multiply straight across by taking our winnings times our probability, and that's going to equal the first part of our formula for our expected value, because the expected value is the sum of our data point times the probability of each individual data point. And then when we add those all up, that's my expected value. So this is the basic formula that we were looking at. So I literally have to take each one of these, multiply straight across, get this number, and it does take a little bit of work here. So multiplying straight across, and then I just need to add them straight down in this last column here. Okay, so when we sum that last column, this is going to tell us what our expected value is. So basically, on average, if we were to play this game a ton of times, we can expect that we are going to average win or lose some money. Okay, so in our case here, when I add those all up, I end up with a negative 0.3820. So we can expect to lose on average 38 cents per game if we were going to play this enough time. When I say enough times, I mean like you've literally played this game all day long. This is all you're going to do. On average, you would be losing about 38 cents per game. Now, this was a nice one because it was a little small, but what happens if I did not give you a bunch of words, but maybe gave you a table? So let's try something else. So let's try, Peyton is trying to decide between two different investment opportunities. Now, the two plans are summarized in the following table. The left column gives the plan's potential earnings, and the right column gives the respective probability. And we want to know which plan should he choose. Okay, so we've got two different probability tables here. And technically, you kind of have to split them in half. So think of it as split it in half there. So this is plan A, this is plan B. Now, when we talk about this, which one should he choose? It's a little difficult to kind of look at this and say, oh, which one's going to earn the most money is going to be the better plan. I don't really know that. On average, we want to know which one is going to be the better. So basically what we're going to do is we're going to determine which plan gives us a higher return, which one gives us more money back or expects to give us more money back by looking at that expected values of each one. So because I technically have two different probability distributions, I'm going to say for plan A, we're going to use X sub A, and for plan B, we're going to use X sub B. Now, we're going to use a calculator method for this. So I've already showed you by hand, so let's do our calculator method. So anytime we talk about these types of things, the step one that we're going to do is we are going to literally say stat, edit, put this stuff in the calculator, and we're going to list our earnings in list 1 and probabilities in list 2. Okay, so let's use our calculator. So again, our first thing is we've got just plan A. I'm only going to look at plan A right now, and then I'm going to show you plan B. So with our plan A, pulling up our calculator, we're going to hit stat and edit. Okay, everybody should see all the lovely numbers in there. I do suggest take a good quick look as you go through these. Verify to make sure that you did enter in everything correctly. If you don't, you're going to get a wrong answer, and you're not going to understand why you got a wrong answer until you go back and check. So verify that, make sure everything is in there correctly. Also, make sure that you are using the negative symbol. A minus sign will not work here. The other thing is make sure that these line up. They should be perfectly symmetrical there. Once you've got them in there, stat, over to calculate, one var stat. Make sure that for my TI-84s, you should see this beautiful screen here. It should say type in list 1 and list 2. Make sure that the calculator knows that we're using two lists here and click calculate. For my students that have the TI-83, remind yourself that it should be list 1 comma list 2. Okay, so make sure, again, you have to tell the calculator how many lists to use. And then you'll get that same VARSTAT list just like this. So as you look at that one, remind yourself, remember we talked about our expected value is the same thing as X bar. And so there we have our X bar is 24.5. So we kind of know that basically our expected value, or X bar, the mean, is 24.5. Okay. Now, once you do this again, guys, you will have to repeat the exact same process for plan B. So you literally have to do the same thing again. So stat, edit, put everything in list 1 and list 2. Then you're going to go to stat, calculate, run your one var stat, again, making sure that it's using list 1 and list 2, and then you're going to get a different mean. And again, these are going to be the screenshots that you should see when you run it. And again, for those of y'all with your nice, lovely TI-84s, this is kind of be what you see here is your TI-84s. This screen here, this is going to be for my TI-83s. Okay. If you have a TI-84 and do not see this screen, guys, just fall back on to what the TI-83s say, because if you have a TI-84 and it doesn't show you everything, then the TI-83 will be exactly the same as what you had. Okay, now as you guys look at these here, that's pretty much what my two answers are. So I got 322 and then I got 2450. So from these calculations, we can see that the expected value for plan A was $24.50, and the expected plan for part B, our expected value was $322. So it really feels like plan B is the wiser choice, because I'm expecting to earn more money on average in the long run. Okay, now let's talk about variance. Now, variance and standard deviation, we've looked at these before. And again, really the biggest part that we want to remind ourselves with these ones is not so much necessarily these formulas. Again, we want to remind ourselves of these symbols attached to the words. Okay, now you can still find a variance in a standard deviation, but do I need to memorize these formulas? No, you don't actually need to memorize these formulas. We can actually learn the calculator method, but again, you really want to place more reference on what your symbols mean and what they are connected with. So when calculating the variance or standard deviation for a discrete probability distribution, again, you're going to have that rounding where you round more than the largest decimal place in your values. There are some occasions where this exception to the rule is. Also, if you are, when calculating your variance, do not round that standard deviation before taking it and squaring it. Okay, so where would I actually use standard deviation and variance? Well, which investment plan in our previous example for plan A or B carries more risk? Now, being riskier means that on average, my risk is going to be further apart. So how far it is away from the mean for the different values I could get would be more likely a standard deviation. So to decide which plan carries more risk, that's going to lead into finding that standard deviation. So, but also while we're at it, let's go ahead and calculate out the variance for each investment plan itself. Okay. Now, to do this by hand, you would use a table and organize it, and it's a very long process. For us, I'm going to show you guys using the calculator method here. So using our TI-84 plus to begin us off right away is you kind of need to remind yourself what plan A was. So again, I'm going to pull it open here, and I'm going to go back into stat, edit, put my stuff in the list there. Once you've got it in the list, remember you're going to go to Stat, Calculate, and 1var Stat. Make sure that it says List 1 and List 2, and you should get this lovely screen here. For my people that do not get that beautiful menu pop-up, but you have a TI-83, remind yourself that you have to tell the calculator it's List 1, List 2. Okay, run it, and you should get this beautiful thing here. Okay, now as you guys are running all this list stuff, one of the things that we begin to notice is that pretty much what we have is everything we need right here. And when we run this list, the standard deviation is right here. Okay, so this is my beautiful standard deviation. But again, we are going to round it. We are referring to this in money, so I was going to round 2 decimal places here. So this is kind of where that exception to the rule is. Even though most of my data only has basically 1 decimal place, it is referring to money. So that's why I know I'm going a little bit different in that respect there. Okay. But what I do have here is that as I take a peek at this, that's just my standard deviation. How do I get my variance? Okay. Now, as you do your variance here, please understand there's multiple ways to do this. If you are not as familiar with your calculator, you're going to want to kind of write down what that actual variance is, what the standard deviation is to be able to get your variance. So you can literally start typing in that number 869.3228687. And then take that and square it. Again, don't round early. If you round early, you're going to get the wrong answer. And then we get this beautiful number here, right? Or, guys, remind yourself, I taught you that there is a way to be able to get that variance without having to write that whole number down. VARS, number 5 for statistics here. And then we are looking at the standard deviation, so number 4, and squaring it, and you'll get that same answer. And you didn't actually have to write down all of that information. Okay. Again, as you guys are looking at it, those are going to be the same steps pretty much every single time. Is step 1, stat, edit, put all the stuff in the calculator, then stat, calculate 1var stat, making sure that you have list 1 and list 2, and looking for the standard deviation. Again, these 2 things down here at the very bottom are going to be the 2 different menus that you see. And this is going to be for my nice, lovely, this is for my TI-84s. This is for my TI-83s. If this menu does not pop up and you have an 84, this works for everybody. Okay. Now, once you have that and you've got your standard deviation, and again, you're just taking a peek for that symbol for the standard deviation there, you can take a peek at it, and we can do that now for our variance. We just need to take that standard deviation and square it. So again, VARS button, number 5 for statistics, look for the symbol for the standard deviation, so number 4, take that, add the power 2 on it, and there you have it. Okay. So what do those actual results tell me? Well, those results tell me that by comparing the standard deviations, we see that not only does Plan A have a higher expected value, but its profits very slightly less than those of Plan B, because Plan B is going to carry a slightly lower risk than Plan A because, again, that standard deviation is not as far away. Remember, a standard deviation is on average how far something is away from the mean. Okay, and that is 5.1.